Thank you. And let's do a share screen. Okay. Can you see my screen? Repeat. Can you see my screen?
Yes.
Very good. I don't hear you very well. I don't know if you don't say anything or that I just don't hear you. Just trying to organize things here. Okay, that's really good. Okay. So let's do a recap. So we are talking about the Schwarzschild solution to Einstein's field equation, right? So ds squared is just minus 1 minus 2 gm over r dt squared plus 1 minus 2 gm over r minus 1 dr squared plus r squared d omega squared. Okay, this represents the metric that provides a solution to Einstein's equation in vacuum r mu nu equal to 0. Right? We saw that this metric has two interesting points. One of them is at r equal to 0. One of them is at r equal to gm. Over c squared if you are to put the units properly. R equal to 0, this is called the singularity. R equal to gm, this is called the Schwarzschild radius, or the event horizon. From reasons which will get more and more clear as we discuss. But before we digging deep into that, we are first considering the motion of particles in the Schwarzschild geometry. So last time we saw the following. I have to slightly shift things here so that I don't run over the cables here. All right, so we saw that we can try to solve the geodesic equation, and we can write down the geodesic equation. It's just going to be particularly annoying and not very helpful. Instead, we use the Killing conditions. We saw that the fact that the Schwarzschild metric has 4 symmetries, right? 1 related to translation around time, and 3 related to rotation, right? Around all the 3 axes. By the way, the fact that the symmetry is related to a conserved physical quantity attributes to whom? I'm sure you heard the name. That's a theorem in mathematical physics, which is attributed.
If I'm not
Sorry?
mistaken. Netto?
Netter, yeah, Amy Netter, one of the most famous women in science. That's Amy Netter. So to every conserved quantity, every symmetry, there is a conserved quantity. So the conserved quantity associated with the time symmetry is energy. Conserved quantity associated with rotational symmetry is, of course, angular momentum. What's the conserved quantity that would be associated with translation symmetry in space? Come on. Just use your imagination for a second. There would be a linear momentum. If I can move in space freely, that means that my moment, and without affecting anything, that means that my linear momentum is conserved. Right? Now that's not the case here because there is a singular point. So if I go along the space and I'm changing my radius from this singular point, right, r equal to 0. Yeah? You with me? You know what I'm talking about. Okay, and then we said we're going to use Killing conditions, right? So k mu dx mu over d lambda is equal to 0, and as well as the metric compatibility. Still not happy with the way it's all here. Metric compatibility. Let's stay. G mu nu dx mu over the lambda dx mu over the lambda is equal to minus epsilon, where epsilon is just 1 for massive, and 0 for massless particles. Right. And then we saw that when we write down these Killing conditions, we can associate one conserved quantity with a translation, right? So it will be the time. So the Killing vector associated with the time translation, right? It's just k nu, just minus 1 minus 2 gm over r, and 0, 0, 0. Then the associated conserved quantity, we call it the energy. K mu minus k mu dx mu over the lambda is just 1 minus 2 gm over r dt over the lambda, and we call this the energy. Although the way we treat things, this is simply a conserved quantity of the metric. We call it energy because we know it has all the properties that we need for the energy. The same conserved, the other conserved quantity is, of course, the angular momentum, like L, which is just, L mu is just 0, 0, 0, 1. And then again, L mu is just 0, 0, 0, r squared sine squared theta. And for sine theta equal 1, then we get that L is just r squared d phi over the lambda. And then we said that, you know, looking back at the Schwarzschild metric, we can write down this metric compatibility in the form of minus e squared plus dr over the lambda squared plus 1 minus 2 gm over r times L squared over r squared plus epsilon is equal to 0. This equation from here, that's this form. And this is a very nice equation because it resembles the type of equation that we did, which I hope you refresh your memory over the weekend, right? In your first year, when analyzing essentially trajectories in a potential, any potential, particularly that led to Keplerian motion. Right? So we had a 1D motion in a potential v of r that looks like 1/2 dr over the lambda squared, right? That's the kinetic energy. Things here, plus the potential v of r is equal, of course, the energy, but here it's going to be equal to e squared over 2. So e squared over 2 is the energy. And v of r is 1/2 epsilon minus epsilon gm over L, over r, sorry, plus L squared over 2r squared minus gm L squared over r cubed. And then, after refreshing our memory, we recall that what we have in the first 3 terms here this is identical to the Newtonian potential. And it's only the force term that is different between the GR and the Newton. That makes one hell of a difference. And this is an exact calculation. Again, what we have here is an exact solution. I did not have any expansion or anything. This is the exact solution. This is the exact equation that the particle fulfills in when moving in a Schwarzschild metric. Okay? When we treat E and L as constants of motion. Now the thing to remember, and that could be something which I don't know if you put enough emphasis on that in the first year, right? This is really describing, right, the motion and gravitational potential, right? So, but only the radial part. It's not the full motion, of course, because for the full motion, we also have to have the theta and the phi part. Theta, we use the conservation of the direction to argue it has to be in a plane. So we don't need to worry about that, but phi, of course, changes, right? So the trajectory that we're looking at, right? So if we have a source of gravity here, right, then the motion can be either closed, like an ellipse, basically. But again, we're only looking at R. Right, so if we put trajectory as a function of lambda, we're only looking at R of lambda. And the same if the trajectory is open. Well, it's an open trajectory, and again, we specify the trajectory as a parameter of lambda, and we're looking at R of lambda. And of course, to get a full equation, we have to get a full solution, we must have also phi as a function of lambda. Right. But it doesn't matter, right? We can still get the answer. And then when we plotted the potential, right, I just reminded you that if we're just looking at the Newtonian potential, then we had basically, there are 4 cases, right? So the first case is Newtonian massive. That is epsilon equal to 1. This is something which you're familiar with, because there is nothing here that is different than what you did in first year when you analyzed Keplerian motion, right? And then we looked at the potential, and the potential as a function of L. So that's R, and that's V of R. 0, 1. Right? So as a function of L, it would look something like that. I think that's the word 1/2 when R goes to infinity. And the exact shape depends on L. This is for L equal to 1. And the types of trajectories that we have, are either open, so particle gets close in, and then get to the minimum radius depending on the energy versus the potential, right? The effective energy. So in reality, this corresponds to a trajectory that goes something like that. And of course, this would be our mean. This is our mean. And then we have elliptical trajectory, which is bounded between R1 and R2. So you can simply plot R1 and R2. And the trajectory would look like an ellipse with these 2 extremes, right? Another procession, like I'm plotting it here. You got it, yeah? Or if it's in the minimum of the potential, or bar, then of course it's going to be a circle. Right, so if this is R bar, the trajectory is going to be a circle. A real circle, not like I'm plotting here. Now this all I believe that you've seen before and you've learned that, and so there's no real issue. Right, and these are all parts of conical cuts. If you've seen that, if you're not, then it's a good time to bridge this gap. Now, when we looked, so this was the first case, right? Newtonian massive. The second case was GR massive. So again, epsilon is equal to 1. Now we need to take into consideration the full part of the potential. So again, at large radii, this last part does not contribute much because it's the smallest, right, for when R is large, but it has a huge effect when R is small because the minus sign here, it gets the potential to minimum. So when I plot the potential, then again, at R equal infinity, that asymptotes to 1/2, but when R is equal to 2, it always goes to 0. This is something which you can easily see. And then, depending on the values of L, if you draw the potential, it will look something like that. Something of that kind. Particularly good drawer. So this is for L equal to 4. So here there are two minima. So there are two extremum values, right? There's one extremum value, some values are here, and another one at some values here. And from the potential, it is clear that one of these extrema is a minimum, one is a maximum, which means practically that one of those is stable, so it is stable, and one is unstable. And the types of trajectories that one can have, right? If a particle is exactly here or here, right, R1 and R2, then it will obey a circular orbit. R1 will have a circular orbit, and also at R2. Of course, the difference is that since it's the radius at R2 is stable, that means that if there is a small perturbation, then it will return back to where it was. But in R1, if there is a small perturbation, right, it will just increase the perturbation until eventually it will either fall inward or go back outward. Which means that in reality, when we look, when we use a telescope and we look outside, then we expect to see objects only at R2. If there happens to be an object at R1, we don't expect it to stay there because any small perturbation will take it away from there. Now, similar to the Newtonian potential, so this is for the minimum, we can have a situation where the energy is such that it is bounded between two radii, or mean and R max. So we have the same situation that we had in the Newtonian potential. But there is a new type of trajectory. By the way, another difference is that in GR in general, the trajectories are not simple cuts of the cone. And we have the unbound trajectories. So the unbound trajectory here, this is a pink one, is back in, no, it can represent something that looks like that. And we have a new type of trajectory that did not exist. in which the particle gets close enough, crosses the barrier, and just falls back into zero. So we'll represent a trajectory that goes something like that, and then just spiral in and we sink in. This is something that does not exist in Newtonian gravity. And then we also show that, okay, we can find out exactly these locations of where the radius becomes circular, or circular would be depending on the angular momentum L squared over GM and 3GM in the limit L goes to infinity. And then these are the two ones. So we have this concentration here at R1 will go to 3GM. And then when L decreases, the angular momentum decreases, then we have that the minimum value of L can be square root of 12 GM, in which case RC minimum or L minimum is just 6 GM. That's called the R ISCO, innermost stable circular orbit. And I mentioned that this is something which is of particular importance because this is something which we can see. Because what happens in reality is that when we have a source of gravitational potential, such as a black hole, since there is a lot of gas, or typically what happens is there is a companion star that its envelope is full of gas, and this gas can be emitted from the star and be attracted by the gravitational potential of the black hole, or another small object could be a neutron star, compact, not small, sorry. What will happen is that this gas will just start spiraling around it, forming a disk. Since there is a friction, then it will gradually loses angular momentum, and the disk will just get closer and closer in. Of course, some parts of the gas will flow outward because angular momentum has to be conserved, and many will fall in, but it can only occur until this ISCO radius. Now, since as the gas falls in, it gets hotter. Again, it's simple friction. Then it emits radiation at higher and higher frequencies. So what we see is the X-ray emission. And the X-ray comes from this ISCO, innermost stable circular orbit. Another thing that we can see are specific emission lines, typically the iron lines, which are observed at 6 keV. Again, it's an X-ray. So we can actually get a good measurement of the radiation, which mostly come from close to this ISCO radius. So just that you know, in case you're interested in becoming an astronomer one day. Okay, I think this is as much as we did last time. Any questions before we proceed? The reason why I spent about 20 minutes reviewing that is because although these things are by large things that I believe you've seen in first year, I somehow had a feeling that it's not going to be a bad idea to have a review on that, just to make sure that everybody is kind of remembering what we had in first year, right? You agree? No complaints? No. Okay. Questions before we proceed? Any questions? No. Okay, so we still have two things to look at, right? So we said there are 4 options here. One is Newtonian massive and GR massive, but we also have Newtonian massless. Right, what is massless? Essentially photons. Right. Also neutrinos, we know that neutrinos today have mass, but it's very, very small mass. So it's we can consider them as massless. Right. Now the treatment is essentially identical to what we did, so there's nothing really new except that now epsilon is equal to 0. So when epsilon is equal to 0, then these two terms disappear. So we really look at L squared over 2R squared when we're talking about the Newtonian potential. So this is particularly simple. So for massless photons, The only thing we have is this term. I'm going to be nice to me. Okay. This is R, this is V of R. Right. So it just goes something like that, right? It's L squared over 2R squared. Looks like that. Yeah. Etc. So obviously there is no minimum. And right, there's only there's no minimum of the potential, right? There's no maximum, it just goes to infinity when R goes to 0. So obviously there's no circular orbits admitted by photons. In fact, the only orbits that photons can have, right, is just straight lines. Right? In Newtonian mechanics, photons are not affected, being massless, they're not affected by the presence of any mass. So what do we have here? When I'm looking at this trajectory in this VR and R diagram, the only thing it tells me, that again, that the radius gets smaller and smaller until some minimum value, and then it gets larger, right? So you can think of this as R mean. Right? But of course, the true trajectory of the photon is just going to be a straight line, right? And again, what we're really looking at is just the radius. So of course, this is going to be R mean. Okay, this is just R, lambda. Number 1, 2. And of course, from photon comes from infinity, R equals to infinity, goes, R becomes smaller and smaller as it propagates, and then it reaches a minimum, which is here, and then it just continues on, and then R starts increasing. But we're simply only showing that R here, so you don't see the full, but you know how the full trajectory of the photon look like, right? Okay, so that's easy. Now, in general relativity, so that's kind of simple. Now we have the last case, GR massless. So again, the first two terms do not exist, but we still have these two terms here, which again, except from L equal to 0, where V is equal to 0, we have a conceptually different situation because we have this extra minus sign in this last term. And that again leads to the fact, and you can immediately see that for any value of L, when R is equal to GM, you're always going to get a 0, right? Just remove the L, 1 over R cubed and R squared, so that's an R, and then the 2 goes here, so we have 2 GM, right? So again, if we're looking at a potential for a massless particle, namely a photon in GR, no, I don't want to do. Okay, it's R, that's V of R. And again, 2, then as a function of L, the potential is going to look something like that. And it's going to approach 0 at R goes to infinity. It's L equal to 1, and then L equal to 2, slightly bigger, but still approach 0. L equal to 3 would be a bad drawer, but it goes to 0 quite fast, right? Right. So there is a barrier, but the photon can always overcome the barrier. Right. Now, of course, at the top of the barrier, right, there is an unstable circular orbit. Right. So in GR, photons can have circular orbits. Right. And then you can actually see that right away. If we go back to, where did I derive that? Remember that we have that, we had this last time, right? When differentiating the potential, yeah, that epsilon GM RC squared minus L squared RC plus 3 GM L squared gamma equal to 0, gamma 1 GR 0 Newtonian. So epsilon here is equal to 0. Then you end up that RC is equal to 3 GM. So V of R is maximum at 3 GM. So we do have a trajectory of a photon, right? So again, when we look at the trajectories of the photon, we do have a trajectory where the photon just circles the source of gravitation at a precise radius, which is 3 GM. Now we also have the previous trajectory that we had, so a photon can get from infinity and then go back. Of course, what will happen now, as opposed to what we had in special relativity, in Newtonian physics, right? A photon would change its trajectory. It will go something like that. So how can it be? Again, the photon does go in straight line, but now the space-time is curved. And of course, we also have these type of trajectories, which essentially refers to photons that get straight in and then just falling. So that's why I'm pretty sure that you've seen this picture, right? When you talk about GR, you've seen this like a space-time that looks something like that. Right? So now you see exactly what happens here, right? You do have a situation where a photon can orbit like that. Maybe I should have drawn that in green. That's the same trajectory that we have here. Now, of course, the photon goes in straight line. This is not a stable situation. You know, one small perturbation will just fall in or get out. And the red photon does come from infinity, but again, since the space-time is curved, it will just have to shift its trajectory. Right, and the purple photon go from infinity, but then just spiral inward and have to go essentially inward. Now, the important thing to note is that, you know, these photons, they move, of course, along geodesics. So they do move along straight lines. Right? It's the Schwarzschild metric itself that is acting to curve the space-time. Right, questions? Questions? Come on, don't tell me that everything is clear. Everything is clear? Okay, cool. I'm quite happy. You say that in the exam, right? Okay. So so far we told you very nice stories with a lot of math and a little bit of physics at the end. But you know, any theory, as beautiful as it may be, is not considered to be physical before it can be tested experimentally. Behind every successful theory, there is always an experimental test. So the natural thing to do now is to discuss classical tests of GR. Right? And when we say classical tests, what we mean is that think of an experiment whose that can be done, or observation that can be done, whose result can be used to discriminate between the general relativity and Newtonian theory, right? Now, this is a question that I refer to this audience here. Can you think of a test or tests that can be used, whose results are different in the context of relativity and in the context of Newtonian theory?
Lunar Eclipse.
Sorry?
Lunar Eclipse.
How is that different between Newtonian and general relativistic theory?
Because we can see the light of the sun that is bent on the moon.
What is lunar eclipse, by the way? What? I think it might be confusing.
שהירח מסתיר את השמש?
That's called a solar eclipse.
Sorry. אז the opposite.
That's called a solar eclipse. So what?
So the light bends because of the gravitation of the moon, and we can see
the light would bend because of gravitation of the moon.
Otherwise, we can see maybe the.
Well, you know, the sun is very, very, very bright. Right? You cannot even look directly at the sun.
Okay.
You're sort of in the right direction, but I think you're a bit confusing, right? I assume that what you're talking about, I'll call it number 2, is deflection of light. But the deflection is not by the moon because the moon is way too small to be noticeable. Okay, maybe I should give you another hint.
I know that the one with the planes, they took a plane and let it rotate the Earth, and they put a clock in the plane, and they measured the time difference between the clock on the plane and the clock on Earth, and that's how they show the time dilation.
Okay. You have to be a bit careful because if the plane is moving, right, you have time dilation because of special relativity, right? We're talking about general relativistic effect now that we want. I'll actually discuss that in the context of a GPS, so you're right. Okay, maybe I should be a bit more, maybe I did not explain myself properly. Let me just finish writing. Deflection of light by the sun. So this whole theory of relativity, as I told you, was written in 1915. Schwarzschild had his solution in 1916. It was highly unfortunate. You know, this time was a war, World War I. He was fighting he was a German, he was fighting against the Russians, and he got wounded. And I guess today he would simply be killed, but 1916, the medicine was not that great. So he died a few months from his wound. So he didn't live much longer after he wrote his solution. So we're talking about this time of, more than 100 years ago. After Einstein wrote his theory, after Schwarzschild wrote his solution, that people were thinking of whether there is a way of proving or disproving Einstein's new theory. This has been associated with technology that existed over 100 years ago, except for one, which is only 50 years ago. And so, you know, there are what's considered to be there are 4 classical tests of GR, which could have and were, of course, carried. Otherwise, I wouldn't sit down spending all of the semester with you explaining all these nice mathematical tricks. And of course, the GR was found successful in all 4 of them. So what I'm asking you is what within the technological limitations that existed, technology that existed 100 years ago, what type of experiments could have been done and were actually done that could discriminate between the predictions of Newtonian gravity and the predictions of general relativity. So the second one, which I wrote based on what you said, is the deflection of light, but it's not by the moon, it's by the sun. I'll discuss that. It's the second point. But I forgot. What?
Maybe the trajectory of the Hama, of Mercury.
Talking about the precession of perihelion, right?
What is it?
Yeah, you're right. It's called the precession of the perihelion. Of the inner planets. So just as a reminder for those of you who are a bit didn't pay careful attention, a planet moves in an ellipse, right? And the closest point is called the perihelion. Right? The closest point, there's a closest point and the farther away point, right? From it. So now, every orbit, it doesn't repeat itself exactly, but as I go here, right, every orbit is slightly different. No, you cannot see me. But every orbit is slightly different than the one which was just crossing, which means that the perihelion is a slight different location at every orbit. Right? So this motion of the perihelion is called precession. And this is something that you can even say it as a prediction, right? Not a prediction, right? It's something which existed before. People realized now since the late 19th century, there had been accurate enough measurements of the trajectories of the planets, of the location of the planets on the sky, and people would actually measure the precession, or this is the precession of the perihelion of the inner planets throughout the years. And they realized that there is a slight discrepancy between the prediction by the Newtonian theory, which could not be explained. There were various attempts to explain it within the framework of Newtonian mechanics, mainly but arguing that there are some extra planets that we did not yet discover. Right? This actually is the way that we discovered Uranus and Neptune, right? By small deviations of the trajectories of the other planets from the Newtonian theory expectations, right? So here, this is a precession of the perihelion, right? This is something which is different, right, between the GR and the Newtonian mechanics expectations. There's at least one more which I would expect you to say because we already discussed it.
The redshift.
Redshift, thank you. Right, gravitational redshift of spectral lines. We actually discussed that, right? And the fourth one is something which I don't expect you to know. It came out quite later. This came out in the 60s. That's called gravitational time delay. And the other name is a Shapiro time delay, named Irving Shapiro. Irving actually is alive. I actually happen to know this guy. It's great guy. Should be in his 90s. Still very active. So that's known as the Shapiro time delay. Supposed to meet him next year. So hopefully he'll survive by then. One of the coolest guys I've met. So this it's called Shapiro time delay. It's a time delay essentially. Again, when a particle moves or when a photon or a radar signal moves in the vicinity of an object, right? It's not only changing its trajectory, but also changes the time it takes it to go. So you can measure this time difference. Let's discuss that one by one. So these four, these are considered to be the four classical tests of general relativity. So let's discuss them one by one. So the first is called the redshift, right? Gravitational redshift. Again, don't get confused. I told you, when people speak about redshift, there are two separate meanings for the same word. One is a gravitational redshift, which we are discussing now. There is also this thing which is called cosmological redshift, which is something completely different related to cosmology. You end up having a somewhat similar effect. The spectral lines are being shifted to the red, but it has a completely different origin. We will discuss that in something like 2 weeks' time. Or we have time to discuss it. Okay, so to understand gravitational redshift, which is rather straightforward, right? We just go back to the Schwarzschild metric, which is written here. So let me copy paste it. You would be nice to me. Okay, copy paste it. Copy. Aha, if you don't have iPads, then you have to rewrite everything yourself. So essentially, what is gravitational redshift, right? Now we're considering two observers that are static, right? So they're not moving, right? So consider two static observers, right? So we have this point here, right? So we said that one observer is here, another observer is here. Now they're not moving, right? That means if they're not moving, that means that R1, theta 1, and phi 1 are fixed. And the same R2, theta 2, and phi 2. Right? So if I'm looking back at this Schwarzschild, right, this is, you can look at it as d tau, right, the minus d tau. So that means that the proper time, so let's look from the point of view of observer 1, right? So the proper time of observer 1 is related to the coordinate time, right? D tau I over dt is 1 minus 2 gm over r to the power 1/2. Right, for each observer. Right, again, tau is the proper time, and t is the time in which the coordinate, are measured. Now let's suppose that this observer 1, right, so O1, right, emits a pulse of light, right, wants to signal something to his friend, right, which is standing at O2, right. Now, O1, right, measures the time between two successive crests to be delta tau 1, right. Now, each crest follow the same path to O2, right? But now they're separated by a different time coordinate, right? So delta t, that is 1 minus, initially, right? Delta t is 1 minus 2 gm over r, 1 to the power 1 minus 1/2, delta tau 1. Now here comes the thing which is a bit confusing, right? Remember, we have a time-like Killing vector, right? So that means that delta t is not change, right? The separation of delta t is not changed since we have a time-like Killing vector. So the second observer, right, measures in her clock, right? Delta tau 2 is just 1 minus the second observer measure. Delta tau 2 is 1 minus 2 gm over R2, the power 1/2 times delta t. The delta t is not changed, which means that this is 1 minus 2 gm over R2 divided by 1 minus 2 gm over R1 to the power 1/2 times delta tau 1. Right, delta tau is the proper time, right, between the two crests, which means that the observed frequencies is just the inverse, right? So omega 2 over omega 1 of the observed frequencies is just delta tau 1 over delta tau 2, just 1 minus 2 gm over R1 divided by 1 minus 2 gm over R2 to the power 1/2.
No, it should be the opposite, right?
Now, this is the correct one.
Oh, okay. No, it's omega 2. Okay.
It's omega 2, which is 1 over delta tau 2. Now, this is the exact result. Remember, we actually derived that in what's called the weak field limit, right? So, in the weak field limit, now what is the weak field limit? It's R is much greater than 2 gm. Right. Then we had that omega 2 over omega 1 is just 1 minus gm over R1 plus gm over R2, which you wrote is 1 minus phi 1 plus phi 2. So the photon frequency goes down when phi is increasing. In other words, right, what we have is that the photon has to climb through a potential well. Right, it's climbing through a potential well, so its energy goes down. Right, since epsilon of the photon is h bar omega, omega goes down, the frequency goes down. Right, that's why it's called a redshift. The correct way to think of it is, right, as the photon climbs the potential well, gravitational potential well, it loses energy. So frequency, since epsilon is h bar omega, then omega turns into that. Now, what really the origin here, right, is that the proper time, right, delta tau, is a function of the coordinate r for two static observers. Right, so the clocks, the internal clocks of two static observers in Schwarzschild geometry ticks in a different rate, different pace. Okay, that is the cause of this time delay. Is that clear to anybody? Yeah. For some reason, there are less students than usual today. Am I right? For any reason, if you know, or I should ask you because you're here. So. All right, questions? Now, again, this is something that we are measuring. Right? This is something which can be measured, this redshift. When we are looking at, again, accretion disks, when we're seeing iron lines, we can identify the spectral lines, right? And everything is being seen to be redshifted. It's not only redshift, it's also Doppler shifted, because if, when we speak about accretion disks, it's also being rotated. But you can identify the lines and see that they're redshifted. And we know where they mostly come from, right, from the east coast. So they're quite good. Again, it's not exactly, I mean, it is exact. What I said is exact, only that the metric is typically, there is an extension of the Schwarzschild metric called the Kerr metric. So it's slightly more complicated than that. There's not much point in me talking about it because except for having me more, I should be careful. I should say the following. It's mathematically much more complex, and physically there are some interesting stuff happening there, but I'm not sure if it's worth the complexity of understanding how it works. Not in the first course in GR, maybe a second course is more appropriate for that.
Yeah, so, but I have a question. When was it discovered, like experimentally? Because I remember this wasn't the first evidence for the, for GR. I think Eddington was the first one. So.
So you can say it's post-diction, right? Not a prediction. It was this precession of the perihelion of Mercury, because this is something which was known before Einstein invented theory of relativity, and theory of relativity could explain that. What we'll talk about, you know what, the Eddington, I'll tell you in a second about that, because that's going to be the second part. So the deflection of light. When was that detected first? I'm not sure. Not too much afterwards. Okay. I'm not sure exactly when it was detected. I'm not sure the exact year. I can check if you want, or you can check it out. I'm sure it's in Google or Wikipedia, one of those. It wasn't that far off after that, because spectroscopy was pretty much well known at that time, I think. And you could do spectroscopy of stars. No, I'm sure that spectroscopy was well known because it was invented by Kirchhoff in the 1900s, 1860 something. And I'm pretty sure that they use it to measure the composition of stars. And they had the technology back in the late 19th century to actually see emission and absorption lines from stars. That's how people know what is the sun made of. Like nobody went there to do a chemical test.
Okay, I checked now in Wikipedia. They say that in 25 they got the first results, but they were criticized, and they the best result was obtained in 54.
The technology obviously advanced, right? But you see, I wasn't that far off. I mean, 1925 was the first time. Of course, initially there were a lot of criticism, and of course, it's the technology. That is something standard, right? 1954 is 29 years later. Then obviously by then the technology had been much better. But yeah, the first measurement, when you say 1925, I take your word for it. As I said, I don't remember that by heart. Okay. Okay, so that was for the gravitational redshift. The second thing which you just mentioned is the deflection of light. By the way, when I said check in Wikipedia, I didn't mean do it during class. You have plenty of time after class to check it out. But fine. Deflection of light. So yeah, you're right that historically, this was the first independent test made for GR. So, and that is something which is, you know, there is a sharp contrast here between GR and Newtonian physics. Right? Newtonian physics is very simple. Photons always move in straight lines. They don't care about gravity. Right? Gravity doesn't do anything to them because they are massless. And in GR, it's not, right? Now, the measurement that I think Jonathan might refer to is something that is slightly different, right? What the gravitational potential that we're really looking at is the gravitational potential of the sun, right? So this is the sun. If you can see it, blue, right? Yellow, and this is Earth, right? And the Earth rotates around the sun. So what are we really looking at? There is a moon, but we don't care about the moon. The moon doesn't really play much role here. So what we're really looking at is emission of light from distant stars. So various stars at infinity, right? And when we're looking at the night sky, we're looking at these stars, right? Now, by that time, we're talking about 1919, right, or slightly before that, people started to use plates, right? The technology for photography became more and more mature, right? So initially, before that, people were simply looking at the telescope. You know, telescopes were there since Galilean time, but they had no way of, you know, taking pictures because the cameras were only invented by the late 19th century, right? By that time, what they did, they could attach the camera to the telescope. Now, when you attach the camera to the telescope, now you can take an image, which is now stored on a plate, right, a photo plate. So the whole point was, okay, so you look at the stars. Of course, in order to look at the stars, you need to be in the night. So when we're here, we're looking at the sky, at the stars, and we put them on a photo plate, right? And on that plate, we're seeing all these stars and we store them. And then half a year later, the Earth is on the other side of the sun, right? 6 months pass. The Earth is on the other side of the sun. Now, of course, we cannot see the same stars because the sun is too bright. So, you know, it will be during the day. Now, here is when we had to go through the lunar eclipse. So when there was a lunar eclipse that covered the sun, then we could take another plate and take pictures of these same stars. Now, what do we expect to see?
Stars in different location because of the gravitational curve.
Exactly, right? So they go in straight lines, right? Now, when we're on the other side, right, they go in straight line, but when they have to go close to the sun, there will be a slight deflection. And so the relative location of the stars relative to each other is going to be different. And since we already had these plates, we can now simply take the plate, take the picture that we took half a year ago and compare them one-on-one. So we can tell what are the exact locations. It's not something which we made by eye saying, oh, it's somewhere over there. That's actually how people used to work before the time of cameras. There was nothing better. Well, there were all sorts of very interesting inventions, but they were not as good, obviously. Now, the theory behind that should be quite straightforward, right? Because we actually derived that even today, right? So if we go back to the theory, right? Remember when we spoke about light rays, right? We had half dr over the lambda squared plus v of r is equal 1/2 v squared, and then we had v of r is half epsilon minus epsilon gm over r plus L squared over 2r squared minus gm L squared over r cubed. So now we're talking about light. So when we talk about light, then obviously epsilon is equal to 0, and we can neglect these two. And so we have from these two, we have 1 over L squared, dr over the lambda squared, basically multiplied by 2 over L squared, plus 1 over R squared, minus 2 gm over R, is equal E squared over L squared. So using that, we can define what's called the impact parameter. B is just L over E. And then using L, just R squared d phi over the lambda. And then we can write it down as d phi over the R is equal plus minus 1 over R squared, 1 over B squared minus 1 over R squared minus 2 GM over R to the power minus 1. So just to get, do the algebra, it's pretty straightforward. So just to get a feeling of what happens, right? So this is the source of gravity, right? This is the photon. It's coming from here and is being deflected. So so this is B. Right? This is R. This is phi of R. This is delta phi. This is a deflection angle. This would be R mean. Now to get that, it's just a matter of integration. Right? So to get delta phi, one needs to integrate just twice times integral from R mean to infinity dr over R squared of that essentially 1 over B squared minus 1 over R squared and minus 2 gm over R minus 1 half. Okay, I have to admit that this is a bit ugly integral, which I don't have any wish of solving it. But the one who does it for you is Hartle. I will just mention, so I'm going to copy the result from Hartle, and I'm going to actually send you to Hartle to do the full, to look at the full calculation. Right? Hartle is one of those textbooks that I recommended. I should just say that, you know, in order for light ray to be deflected by the sun, then obviously this impact parameter B cannot be smaller than the radius of the sun, right? Because otherwise this light ray will just go straight into the sun and we won't be able to see. So condition, or practical condition, for a light ray to be deflected by the sun, it must have it be greater than the solar radius, 7 times 10 to the 10 centimeters. That means that the maximum deflection that we can get is that 2 gm sun over C squared V is smaller than 10 to the minus 6. Now, in that case, when this is small, you can do a Taylor expansion. Which is, again, doable. I'm not going to go through it. I told you this you can find in Hartel. So just go to the book of Hartel and you find the full derivative there. And then you find out that delta phi is phi plus 4gm over d. And, okay, sorry. This is delta phi, this is delta phi. So delta phi deflection, the actual deflection angle is delta phi minus phi. So it's approximately 4gm over b. Just to put the right units, it should also be a c squared. So it's a quite small deflection. No, it should be, it cannot be larger than it's 1.75 arc seconds in the case of the sun. Right, just as a reminder, right? So there's 1 degree, and each degree is angle, right? Each degree is divided into 60 arc minutes, and each arc minute is divided into 60 arc seconds. It's quite small deflection. But it is there. So let's actually do something. So just before this class began, I played a little bit with Google. For a second to stop sharing. Now I'm going to do a share screen. I'm going to share my desktop with you. Can you see my desktop now? Yeah. What do you see here? What is that? Try to enlarge it, I don't know how. Do you realize what we're seeing here?
Planets, maybe?
No. This is the BBC.
This is duplication of the picture.
Yeah.
The way
yeah.
bend and the eye continue the line of bending, and you see the picture at a different place.
Exactly. This is exactly what I showed you. So, Einstein became famous. So he wrote all that in, 1915, 1916. 1919 was 3 years later, was the famous solar eclipse, which was not seen in Europe or in the US. It was seen in South Africa and in Africa, in West Africa and South America. And so Einstein, the leading astronomer at the time, which was Arthur Eddington, he set up an expedition to go to the coast of West Africa and of Brazil to take photos, and of the sky during the solar eclipse. And these are the plates that he put. And then there was a second plate, which was taken, I'm not sure if half a year later or half a year earlier. I didn't go and check that. And what you see is, again, a replica of the composite picture. And you're seeing these, these two represents the same star, of course, right? And you can see that they're all the same stars that are being deflected. And the deflection is, again, a function of the distance from the light ray from the sun itself, which, again, I guess this is just put by hand, but I'm less sure about. And, after that observation, after they returned back to England and did the analysis, that's when Einstein became a hero. That's when people realized that, there is no way that, that this could have been done, within the realm of Newtonian gravity. That's exactly the prediction of general relativity. So again, I don't think this is the original one, but this is a replica which was shown by the BBC. Now, if we go a few years earlier, later, many years later, actually. Now let's go to the 21st century. What you see here is, what do you see actually? What is this image? What did I show you here? What am I showing you here? What do you see here?
The galaxy in the middle.
Sorry?
The galaxy in the middle and like bends around it.
Right. So it's not the galaxy. This is called the Hubble Deep Field. This is the Hubble Space Telescope, right, which launched in 1990. And it's still there. And Hubble Deep Field, meaning that, it's looking at various objects, and this is just looking at the sky, staring at the sky for a while, and that's what you're seeing. Now, what you're seeing is an effect which is essentially the same effect. This is called gravitational lensing. What I particularly want you to see are these arcs, right? You're seeing these arcs here, right? What the Hubble Deep Field is showing, right? So there's not a single galaxy, there is a cluster of galaxies. Galaxies tend to come in clusters. And these clusters of galaxies have a very significant gravitational potential. And behind them, there are other galaxies. And what you're seeing is the bending of light from these further away galaxies, from the other galaxies behind them, as they go through the gravitational potential of this cluster of galaxies. Right, so if I do now stop sharing just to go back to the drawing board, and let's do a share screen again with my iPhone, iPad. Yeah. Okay, now you see it, right? So there is this cluster of galaxies here. We are the observer here. And there is another galaxy, a red galaxy. And of course, light from this galaxy is being bent and it's seen to us. And you're seeing this crescent shape. This is called gravitational lensing, because it acts like a lens essentially. Now, in fact, if I were searching slightly more, I could have found this, if the gravitational potential is roughly spherical, which it never is really, and the galaxy is located straight behind it, then you can see that the light from the same galaxy goes from both directions. And what you'll see on your sky, right? How would it look like on the sky? If I'm looking now at the plate, what will I see?
Two spots at the two sides of the galaxy.
Well, two sides is in 2 dimensions, but we're living in a 3-dimensional world. Okay, so this is
cloudy.
Right? What you'll see is a ring. Right? If it's located exactly behind, because it goes through all directions. Right? This ring is called Einstein Ring for obvious reasons. So, after the class ends, don't do it now, but after the class ends, go and Google Einstein Ring and you see various nice pictures. And that's exactly what it is. Now, this we can go over on that quite a lot, because there's gravitational lensing, which enabled us an independent measure of the gravitational potential of this cluster of galaxies that stands in the middle between us and the distant galaxy. It also makes this image of the distant galaxy much brighter, so we can actually study this distant galaxy in much more details than we could without it. And there is also the thing which is called microlensing, which is a small deflection, not full deflection. There's a whole industry of people working on that, studying galaxies and studying the distribution of matter in the universe using this gravitational lensing. But you got the essence. The essence, we just put all the theory here. You got you understand what it is. I hope you do. All right? Yeah? That is, this is gravitational lensing. Okay, we said there are four classical tests. We spoke about two. The third one is the precession of the perihelion. Again, just a reminder, right? So we said that since the gravitational potential, and GR potential is different than the Newtonian potential, there it is, then the perihelion, right? So the innermost, so the point of closest approach in a planet orbit to the sun precesses with time. And it does so in a way which differs between, so this is the perihelion. This portion is called the procession. And it does that in a way which is different than the prediction of Newtonian gravity. And the reason is quite simple, because we have this extra term in the potential, right? Because of this extra term in the potential. And this extra term, as you see, goes as 1 over r cubed, which means that the further away you are from the source of the potential, then it becomes less and less pronounced. So that's why it's most easily observed when we're talking about the inner planets. Of course, all the planets have it, but it becomes more and more difficult to measure. So again, this is kind of, this is the practical reason why people speak about the precession of the perihelion of Mercury and possibly Venus, simply and all of the planets do it, but we simply cannot measure it. The basic picture of how to solve it should be quite straightforward, though the calculation itself is very technical. Right? You basically have to solve for d phi over the r. Right? What we have here is d phi over the r. So phi, we say theta is fixed, so just d phi over the r. And then we simply have to integrate over the successive turning points. So essentially, it is a very similar equation to this one. We just have to integrate between two turning points, right? And it's not light, so it's a planet, so we have to put epsilon to be equal to 1. Again, so for phi dr, and like similar to light deflection. And then integrate between successive turning points. So again, I'm not going to do it. 2 textbooks actually do it. It's just a lengthy and annoying calculation. So obviously, it's something that you have to do at home. So you can find the calculation in Hartel and in Carroll. And you end up that, again, in the limit of a small deflection angle. So for small deflection angle, or Carroll. In Carroll, it's only the second version of this group. The first one he doesn't do. Okay. So delta phi precession is 6 pi gm over c squared a and 1 minus epsilon squared. Right. You should be familiar from Keplerian. A is the semi-major axis. And epsilon is the eccentricity. So just to get the feeling right, so for Mercury, right, this is 43 arc second per century. 43 arc second per century. But again, the advantage of working with Mercury is that accurate measurements of Mercury's position in the sky existed since middle of the 19th century. So by the time, by early 20th century, there's already been 50 years of accurate measurements of Mercury's trajectory. So Einstein has something to compare with. Now, again, I'm pretty sure this was not his initial motivation, but obviously he was quite happy that the prediction of his theory was consistent with this observation. Right. Questions about that? I didn't go through, I just gave you the answer. I didn't want to go through the calculation because it will just take half an hour of algebra. Questions?
Is it 13 or 43?
43. 43 arc seconds per century. For Mercury. For Venus, it's less. For Earth, it's even lesser, right? One goes is 1 over R cubed. Yeah. The last thing that I said, the last classical test is called the Shapiro time delay. And again, I'm not going to go through all of that. This is something which is much later. This was proposed by Irving Shapiro in 1963, I think, somewhere between 62 or 64. The idea again is the same. Rather than solving for d phi over the r, we're solving for dt over the r. Okay. So remember back. So I don't know if we need to go through that. Just the basic idea, right? So again, when we have a source of gravitational potential, like when we have light that propagates, if it propagates here, it will be deflected, but it will also get slower, right? So that's slower. So that's because the t over the r, or the t over the tau is smaller. So we solve. The t over the tau. So solve for the t over the r. And you get that this is plus minus 1 over v, 1 minus 2 gm over r to the minus 1. And again, 1 over b squared minus 1 over r squared, 1 minus 2 gm over r minus 1/2. What does it mean? Well, if we can send an electromagnetic signal inside the gravitational field, and we can trace it back, right? Then, and of course, if we know the location of the emitter and the reflector, then we can calculate the GR correction for the returning signal. Now, what happens in practice is the following. So this is the sun. This is the sun. And this would be Earth. That rotates around the sun. And the signal is sent to Venus. So I told you this was suggested by Irving Shapiro back in the 1960s. So we send a radar signal from Earth to Venus, which we know pretty accurately where each one is, and record back the time of arrival of the signal. Now we know, since we know the locations, we know what should be the time, and we can measure the difference between that and what we expect from Newtonian gravity. Now, when Venus and us are in the same side from the sun, then the deflection should be minimal, but when Venus happens to be on the other side of the sun, right, then the signal that we're sending should go close to the gravitational potential of the sun and be returned back. So we have the difference between the GR prediction and the Newtonian prediction is the maximum. Venus, Earth. And right, so the emitter is simply radar, and the deflector is Venus, the surface of Venus. And the GR axis time delay delta T, again, this is the axis, is approximately 4 GM over C cubed times log of 4 R the reflector, which is Venus, R emitter, which is Earth, divided by R minimum, R1 squared plus 1. This is the radius of closest approach. Now, of course, the effect is very, very small. Right? We're talking about microseconds over the time it takes the signal to go back and forth to be about 1 hour. So the accuracy needed is of the order of about 10 to the minus 7. But apparently in the 1960s, the technology was good enough, the radar technology was good enough to measure this discrepancy. And here again, I did a quick search on the net, on the internet, so I will stop sharing. Now let me share my screen again. No. And this is how it looks like. This is from measurement in 1970. What you're seeing here are days, right? And this is the time delay in units of microseconds. That sorry, this is the difference in time between the measurement and the prediction from Newtonian theory. This is a measurement from 1970, so as I know. The Arecibo telescope that just died last year, if you heard, after many, many years of service. So this is how it looks like. Again, full agreement between the GR prediction and the observational data. All right. So you can search, again, this is named after the guy who thought of this idea, which is Irving Shapiro, so it's called Shapiro time delay. You search that. Can you see my screen now? So measured in the 1960s. This is the Shapiro time delay. All right. I think we run out of time, actually. Okay, that's what I wanted to tell you about the classical tests of general relativity. I think on next lecture, which will be on Thursday, then we'll actually going to talk about black holes. We're going to decipher them one by one. So you get a good idea of what it is. And it's a promo for next week. It's for next lecture on Thursday, in case you don't plan to be there, but you know what you're going to miss. Questions about anything we said?
Yes, Asaf, what is the main difference between the time delay and the redshift, like conceptually? Because, you know, the redshift is based on a delay in time, which is translated to frequency. So
conceptually, it's pretty much the same. The time delay, the redshift is, you know, there is an emitter and an observer, right? And the emitter and observer are not located in the same location, right? Because if I emit something and I'm, you know, it go back around the gravitational potential, when I see it back, it has the same frequency. It's only when I have a difference between the emitter and observer that I have that there is a redshift. here I'm the emitter and the receiver are at the same location, right? So this is something which I can do independent. Let's say I don't know anything about any emitter, right? Or that the emitter gives me some spectrum which I cannot identify any spectral lines in it, right? So I could be sensitive to uncertainty in my way of understanding physics, right? I don't understand spectral lines. Here I'm seeing a time delay, and you know, I just need some reflector, right? Something to reflect my signal that I'm sending, and I'm seeing it back. So it's independent on any uncertain physics of you know, spectral lines, etc. Right? So
Okay.
that's independent. Thanks. Physics, of course, it's the same physics. I mean, the idea is the same physics, it's the same idea. It's very similar. You know, the way we presented it, it's very similar. We just solve, you know, the same equation, just TDR versus the Phi D. So the equations is the same. It's just a different way of looking at the same metric, but it's an independent one. That's the important thing. And needless to say, I already showed you Einstein's theory passed through all these tests and many more. One of the most tested theories there is, and successfully. Otherwise, it would be a very nice mathematical idea, but would not be very useful. All right. More questions before we go?
I have one question. I didn't understand what you write before in the delta t axis.
Yeah, delta t axis.
In the brackets.
It's written 4gm over c cubed times log of 4 times r, the reflector, which is Venus, r e, which is the emitter or Earth, divided by r1 squared. R1 is the point of closest approach. Right, so this is R1.
And what is the before the 4 RE?
4 times R, so R the reflector, R Venus, right? This is RR, then RE, points of the Earth, divided by R1 squared. All that, brackets, there is a logarithm here, log of that.
לא, לפני זה כאילו, המקדם שלפני כן.
4gm over c cubed.
בתוך הסוגריים,
It's a log, it's a logarithm.
לוג. אוקיי. Sorry.
Okay. Yeah. All right. Sorry for that. Any more? No? If not, then I thank you very much. And I'll see you all on Thursday, I believe, and hope.
Thanks, Asaf. Bye-bye.
Bye.
Great rest of the day and a great day.